You probably picture science as a careful process. Clean rooms, steady hands, somebody in a white coat writing numbers in a notebook. And honestly, that makes sense. That's what it's supposed to look like. Except, some of the most important experiments ever run were done in a garden shed, in a kitchen blender, and in one case, by a man deliberately drinking a glass of bacteria. And the strange part isn't that they were reckless, it's that they worked. So here are 8 real experiments that should not have worked. Some were too primitive. One was explicitly forbidden. A couple got the right answer for completely the wrong reason. And the last one on this list ends with a man poisoning himself, on purpose, and collecting a Nobel Prize for it 21 years later. We're counting down. We start with a stick. Number 8. Around 240 BC, a librarian in Egypt decided to measure the entire planet. His equipment was a stick, a shadow, and a rumor. His name was Eratosthenes, and the rumor was about a well in a town called Syene. On one particular day of the year, at noon, the sun sat directly over that well and lit the water at the bottom. No shadow. Nothing. Which sounds like a fun local fact and nothing else. Except Eratosthenes knew that on that same day, at that same hour, a vertical stick in Alexandria did cast a shadow. A small one, but a real one. 2 sticks. Same sun. Same moment. Different shadows. On a flat Earth, that's impossible. On a curved one, it's just geometry. He measured the angle of that shadow, worked out it was roughly a 50th of a full circle, got an estimate of the distance between the 2 cities, and multiplied. One man, one afternoon, the size of the world. But here's the part the story usually leaves out. He wrote his answer in a unit called the stade, and nobody today knows exactly how long a stade was. Depending on which version he meant, his number lands anywhere from remarkably close to the real figure to about 30% too big. So the most famous measurement in ancient science comes with an asterisk. The method was flawless. The legendary accuracy is basically a coin flip. He was either brilliant or brilliant and lucky, and 2,000 years later we still can't check his homework. Number 7. At least he got to work outside. The next man had to seal himself out of his own experiment and watch through a telescope because his body heat kept ruining it. In the 1790s, Henry Cavendish set out to weigh the Earth. Not estimate it, not calculate it from orbits, actually measure it from a shed in his garden. The setup sounds like a toy. A wooden rod hanging from a thin wire, with a small lead ball at each end. Roll 2 much larger lead balls close to them, and gravity should pull the small ones over, twisting the wire by a tiny amount. Measure that twist, and you can work out how strongly matter pulls on matter. From there, you can work out how heavy the planet is. The problem is scale. The force he was hunting is unbelievably small. A draft would drown it. A warm hand nearby would drown it. So he sealed the apparatus in a room, drilled a hole in the wall, and observed the whole thing from outside with a telescope. He wasn't being dramatic. Standing next to his own equipment would have generated air currents strong enough to destroy the measurement. His result for the density of the Earth was 5.48. The modern value is 5.51. He was off by 0.5%, using lead balls and a piece of wire, in a shed. And there's a detail that makes this better. Cavendish was famously, painfully shy. By most accounts, he barely spoke to people and communicated with his own household staff by leaving notes. So the man who couldn't bear to be in a room with anyone weighed the entire Earth, specifically by making sure he wasn't in the room. Number 6. That experiment worked because someone removed himself from it. The next one worked because someone was given a task that was supposed to be pointless. In 1909, the accepted picture of the atom was a sort of pudding, a soft blob of positive charge with electrons scattered through it. Nothing hard, nothing dense, nothing solid enough to stop anything. To test it, Ernest Rutherford's lab fired alpha particles, tiny fast fragments of atoms, at an extremely thin sheet of gold foil. Under the pudding model, they'd all punch straight through with a slight wobble. It was such a safe prediction that the actual counting was handed to a junior Ernest Marsden, essentially as a training exercise. The counting, by the way, meant sitting in a completely dark room for hours, waiting for your eyes to adjust, then watching a screen for faint individual flashes of light and tallying them by hand. And in the middle of all that tedium, Marsden saw flashes in the wrong place. Particles coming back. Not deflected slightly. Bounced. Rutherford said it was about as believable as firing a 15-inch artillery shell at a sheet of tissue paper and having it come back and hit you. The explanation broke the model completely. Almost all of an atom's mass is crushed into a nucleus at the center, thousands of times smaller than the atom itself. Everything else is empty space. If a nucleus were a marble, the atom around it would be roughly the size of a stadium, which means the chair you're sitting on is mostly nothing, holding up a person who is also mostly nothing. And the structure of every atom in your body was found by a student doing an exercise his supervisor expected to produce no result at all. Number 5. That experiment succeeded by finding something unexpected. This next one succeeded by finding absolutely nothing. In 1887, physics had a problem. Light travels in waves, and every wave anyone knew about needed something to travel through. Sound needs air. Ripples need water. So light needed a medium too, filling all of space. They called it the ether. If it existed, Earth is plowing through it constantly. So light fired in the direction of Earth's motion should behave slightly differently than light fired sideways. A wind, but made of nothing. Albert Michelson and Edward Morley built an instrument to catch it. A stone slab floating on a bath of liquid mercury so it could rotate without a single vibration, in a basement, with light beams split apart and recombined so precisely that even a hair's width of difference in travel would show up as a visible shift in the pattern. They rotated it. They watched. Nothing. They checked the equipment. They tried different times of day, different seasons, in case Earth happened to be moving with the ether at one moment. Still nothing. No shift, no wind, no ether. At the time, that felt like failure. They had built the most sensitive measuring device on the planet to detect something, and the something refused to exist, except that nothing was the answer. Light doesn't need a medium, and its speed doesn't change no matter how you're moving. That impossible little detail is the foundation Einstein built special relativity on 18 years later. Michelson became the first American to win a Nobel Prize in the sciences for an experiment that measured zero. Number 4. So far, the equipment has been impressive. Now it gets domestic. By 1952, biology had one enormous unanswered question. Genes exist. Whatever they're made of, that substance is the instruction manual for everything alive. So what is it? Most scientists backed protein. Proteins are complex, built from 20 different building blocks, clearly sophisticated enough to store information. DNA has four repeating units. It was widely considered too simple, too boring, too stupid a molecule to carry the code for a living thing. Alfred Hershey and Martha Chase settled it using a virus that attacks bacteria. These things land on a bacterial cell, inject something into it, and hijack it into building copies of the virus. Whatever gets injected is the genetic material. That's the whole logic. So they grew 2 batches. One with radioactive sulfur, which shows up in the protein coat but not in DNA. One with radioactive phosphorus, which shows up in DNA but not in protein. They let the viruses land on bacteria. Then they needed to shake the empty shells off the outside of the cells without destroying the cells themselves. Their solution was a wearing blender, a kitchen appliance, the same category of object people use for smoothies. The sulfur stayed outside. The phosphorus went in. DNA was the answer. But here's the honest version. The experiment was messier than the textbooks suggest. Roughly a third of the labeled DNA turned up where they wanted it, not all of it, and the two of them were noticeably careful in how they worded their conclusions. And it wasn't even the first proof. 8 years earlier, Oswald Avery and his colleagues had shown the same thing with cleaner chemistry, and the field mostly shrugged and carried on believing in protein. Which means the most important result in 20th century biology went to the version done in a blender. because the version done properly was too quiet to be heard. The blender is now preserved in an archive. Avery never got a Nobel Prize. Number 3. Nobody has been hurt yet. That ends here. Philadelphia, 1804. A medical student named Stubbins Efforth is convinced that yellow fever isn't contagious, and he decides to prove it in the most direct way available. Yellow fever patients, in the last stage, vomit a black substance. Efforth collected it. He started by cutting his own arms and pouring it into the wounds. Nothing happened. So he escalated. He dripped it into his eyes. He heated it and inhaled the fumes. He smeared it on himself. He moved on to blood, saliva, sweat, and urine from patients. And finally, having exhausted the alternatives, he drank it. Undiluted. He didn't get sick, not once. He wrote it up as his doctoral thesis, argued that yellow fever could not be passed from person to person, and got his degree. Now, the reveal. He was right. You can't catch yellow fever from a patient's fluids. And he was completely wrong about why. Yellow fever spreads through mosquitoes, which put the virus straight into your bloodstream, something nobody would establish for decades. On top of that, his samples came from late-stage patients, by which point the material he was drinking was very unlikely to be infectious anyway. Two separate errors, canceling each other out perfectly. He ran an experiment that could not have proved his point, on a question he'd only half understood, and the universe let him win the argument anyway. Number 2. Firth only risked catching something. The next man threaded a rubber tube into his own beating heart. In 1929, the medical consensus was that the human heart was untouchable. Poke it, and it would stop. Insert anything into it, and the patient would die of a fatal rhythm on the spot. Werner Forssmann, a 25-year-old junior doctor at a small German hospital, thought that was wrong. He believed you could run a thin catheter up a vein in the arm, all the way into the heart, safely. His chief physician forbade it outright. The problem was that Forssmann needed sterile equipment and access to the X-ray room, and both were controlled by a nurse. So he convinced her the idea was sound. She agreed on one condition, that he do it to her instead of himself. He accepted, strapped her to the table to keep her still, then quietly numbed his own arm and threaded the catheter into himself while she was lying there restrained. By the time she realized what had happened, the tube was already inside him. He untied her, and the two of them walked to the X-ray department with 65 centimeters of catheter running up his arm and into his chest. Under the X-ray, he pushed it the rest of the way into the right side of his heart and had the picture taken. He felt almost nothing. A slight warmth. That was it. The reward for proving that the human heart could be reached safely, from the inside, was that his career was effectively shut down. He was criticized, sidelined, and pushed out of heart research entirely. He ended up as a urologist in a small town. 27 years later, in 1956, he was awarded the Nobel Prize in Medicine, long after he'd given up on the field altogether. He proved the experts wrong by performing the experiment on the only patient who was guaranteed not to sue him. Number 1. Which brings us to a man who was told he was wrong for so long that he eventually infected himself just to end the argument. Until the 1980s, stomach ulcers were understood as a disease of stress and acid. Work too hard, worry too much, eat badly, produce too much acid, burn a hole in your own stomach. The treatment was acid-suppressing drugs, taken more or less forever, and sometimes surgery. It was one of the most profitable areas in medicine. Then, a pathologist in Australia, Robin Warren, kept noticing spiral bacteria sitting in stomach biopsies, which was supposedly impossible. The stomach is an acid bath. Nothing lives there. A young doctor named Barry Marshall took the problem on with him and eventually managed to grow the bacterium in the lab, partly because a batch of culture plates was accidentally left sitting over a long holiday weekend, giving the slow-growing organism enough time to appear. They now had a suspect. What they didn't have was proof it caused anything. It wouldn't reliably infect lab animals. You can't ethically give a disease to a volunteer. And the entire field had already decided they were wrong. So in 1984, Marshall had his own stomach examined to confirm it was healthy and free of the bacteria. Then he took a culture grown from a patient, mixed it into a broth, and drank it. He expected it might take years to show anything, if it ever did. Within days, he was nauseous, vomiting in the mornings, with breath bad enough that his family commented on it. A second examination showed his stomach lining inflamed and swarming with the bacteria. He had given himself the disease, from a petri dish, in under a week. He then cured it with antibiotics. And here's the part that stings. That still wasn't enough. It took roughly another decade of argument before the medical establishment fully accepted it, and until 2005 for the Nobel Prize. But the outcome is this. A condition that used to mean a lifetime of medication and sometimes surgery is now, very often, a 2-week course of antibiotics. Because one man got tired of being ignored and drank the evidence. 8 experiments. A stick. A shed. A dark room. A blender. A glass of black vomit. A tube in a man's heart. A cup of bacteria. None of them look like science is supposed to look. All of them are still standing. So the next time you take a pill for a stomach ache, or watch a doctor slide a catheter towards someone's heart on a screen, hold that thought for a second. Science does move carefully. It just very rarely starts that way.